One of the key safety topics that we think is important to present is on electrical safety. I think it's key for a number of reasons. One is it can be fatal if electricity gets where it shouldn't be. The other thing is it's so universally applicable to all of us. As I will teach this course in a room full of people, I'll ask people to raise their hand if they've ever been shocked. And it's amazing how many people have been shocked. It's pretty much universal. Everybody has come in contact with electricity and got zapped. And they talk about the universal stimuli. The when we come in contact with electricity, we don't like it. And we want to get away from that as soon as we can. Well, if we come in contact with it, that means we're at risk of injury and maybe even death from electricity. So this is an important topic, and I'm going to try to talk fast on it because I went a little bit long in the first one, so I'm going to talk faster. We want to start off with a little bit of chemistry or physics. You can argue it either way. And it would be correct. But we want to talk a little bit about atomic structure. If we take something, we break it down to really its smallest parts. If we can call it an element or call it something that we can really identify what it is, it's an atom. And our atoms can be broken down into smaller parts than that. Inside of the nucleus, the center part of that atom, we have protons and potentially neutrons. Um, Outside of that, we also have things called electrons. And electrons have a negative charge. And they fly around the outside. They talk about the electron cloud, and they balance the charge out with a positive charge in from the protons in the nucleus. But electrons are they don't necessarily always stay around. Sometimes they can be shared with other molecules that are out there. Sometimes I can end up with a surcharge of electrons, these charged particles, one place, and they have this potential. They want to go to ground. They always want to find a way to balance out those charges, and the flow of those electrons from one place to another is called electricity. These electrons, like I said, are always seeking ground. They're trying to balance out these charges. And the easiest way to do that is to go to the ground, where it can balance that charge out. Well, we use this potential of more electrons one place from another to do work for us. Electricity is awesome. We couldn't be on these, we couldn't be on this training without a lot of electricity sending electrons across wires, making the lights work in the room, and my monitor and computer and all of those things and what you're watching it on. Electricity is a key part of that, and it is essential in almost everything that we do, that we have electricity. But it's also lethal if it gets in the wrong place, particularly our heart. If it goes in there, it can mess up the electrical action of our heart that makes our heart beat in time. And if it gets in that wrong place, it can really kill me. Okay. So let's talk about just some basics. There's a basic law, and it's this equation here. It's called Ohm's law. V equals IR. And that means the voltage equals the current, or amps, times the resistance. And this relationship is important. You can ask any electrician about it, and they will talk about it a long time. But what we want to talk about are just some basics. Volts. Have a smart guy tell me one time, volts are the push, amps are the punch. So it takes both of those for somebody to have an injury from electricity. The voltage pushes along the amperage. So it's the amps or the power. They're the things that can do damage to us. Many of you out there may have come in contact with high voltage electricity. I know when I was a kid, I touched a spark plug wire on a running small engine. And when I came in contact with that, it didn't have a kill switch on it. And so I was pulling the spark plug wire off to turn the engine off. Well, I got a nasty shock from that. And those types of motors, or your car, will put out tens of thousands of volts, but really low amps. And so it hurts, it startles you, but it doesn't have sufficient amperage to kill you. Well, one thing we didn't talk about in this equation is the R, the resistance. And we measure this in ohms. And in Ohm's law, it talks about how the resistance determines how well electricity travels. Can it go from one place to another? And so we'll move on to the next slide with that, where we talk about conductors and insulators. Some things really allow electricity to travel easily. Other things are hard for electricity to pass through. So in an electrical wire, we're looking at these conductors that are here. Inside of the outer sheath is copper. Copper is a great conductor of electricity. Those electrons will just zoom right down through that, and we can carry those electrons from really across the country. You look at our electrical grid, they travel really easy. Well, in this same wire, it's clad with some plastic or rubber material that doesn't allow the electricity to pass through it very easily. Those are called insulators. Insulators don't allow the electricity to pass, and that's how we're able to stay away from contact from electricity. Okay, these are some pretty basic things. I get it, but we got to ask the question: are you a conductor? And the answer is yes. Each of us, if we come into contact with electricity, it will pass through our body. How well it passes through our body depends on a few things. What is our resistance to that electricity passing? Do I have personal protective equipment on that would resist the passing of electricity? How intact is my skin? Is my skin wet? Would that allow that more electricity to pass? And the answer is yes. Think about our tools that we're using. An aluminum ladder is obviously a conductor. If you come in contact with an electrical circuit with that aluminum ladder, it's going to be a bad day. But what about your fiberglass ladder? Is it a conductor? And the answer is maybe. And I would probably say probably. Because even if it's a really good ladder that's designed to be an insulator, it can be dirty. And if there's dirt on the outside of that ladder, an electrical potential can move through that dirt, and you could be a source of ground to that electricity and cause you serious injury. So we've got to know kind of what we're dealing with. And then we move on. Oh, so you've got an outlet probably in the room that you're standing in right now, unless you're out and about watching this online. You take a look at that outlet and you can see there are three connections that we make when we plug something in. In most cases, we'll have the three prongs. Well, that means there are three wires inside of that box in the wall. And let's just talk about what those wires are. One of those is a hot wire. Call that the line. That's the load. That is the giving the power to the outlet. Okay, that's generally a black wire in a 120 volt outlet. The white wire is what we call a neutral, and we'll come back to that in just a minute. And then we have a ground wire. Ground wire is more of a fail-safe. It protects us if something goes wrong. If we have a short where a conductor gets in, where my hot wire comes into contact with something it shouldn't, it takes that power to ground. It makes it safer, so we don't have current floating around in our building, catching it on fire or shocking us. Okay. Well, let's go back to, or let's ask a couple of questions. So, which of these conductors is electrified? Which one has current on it? Well, we have to understand what a circuit is. When I plug something in, I plug my drill or other appliance into an outlet. Electricity current will come through that wire to my tool. Let's say it's a drill. And I push the button on that drill, and it's going to cause the drill to work. that electricity doesn't just evaporate, it has to go somewhere. So we create a circuit. The electricity comes in through that black wire, but it's going to go out through the white wire. That's called the neutral. And so it's a circuit, has to go out and back. So does that mean that both the white and the black wire can be electrified? And the answer is yes. How about that bare or green wire, the ground? It can be electrified at times too. That's generally only when we have a fault or a failure in our system. But just because it's a bare wire there, don't anticipate that it is free of electricity. And those other two don't touch the conductors. It's pretty simple stuff, but we wanted to make sure everybody understands that. Shocking realities, pun intended on that. About 30,000 people are injured annually, enough to go to a doctor to get attention. About 1,000 people are killed every year from electrocution or an electrical accident in one way or another. And we go back to this overall statement that we're all at risk. Electricity is all around us. You take a look around you, how many outlets are there, and lights and appliances, all of those things, we're all at risk. And so we've got to respect the power, and we also have to monitor it and fix things when we have problems. All right. So here's what some of the injuries from electricity can look like. It could be shock, burns. Electrocution is when that current passes through my heart and stops it from working. It can kill me. Sometimes it's beyond that. I can have significant burns, things like arc flash, and that's where a circuit creates a flash or an arc as electricity jumps from one thing to another. That can cause an explosion. It can shoot out particles, but it can also shoot out really high temperature sparks, and just the gases are heated up there. It can blind me. Arc flash is really a significant hazard to us, and also fires are potentially caused by electricity as well. Okay, so we say in here, well, because I have higher voltage, does that mean it's more dangerous? And in general, the answer is yes. If you touch a 480 volt circuit, you're going to be hurt really bad, um, in comparison to coming in contact with a 120 volt circuit. However, about one person per day in this country is killed from 120 volt power. A lot of people die. Nearly half of the fatalities happen with 120 volts. And most of us have come in contact with 120 volts before. What's the difference? Well, it's where that power gets. And so I've got to respect the power and not be complacent around quote unquote lower voltage 120 volt power. Definitely we're going to respect those higher voltages, but don't just say, it's 120, I'm good. Respect the power. So electrical hazard shock is when our body's in the path of that current. Direct cause can be or result from this contact can be electrocution. It can kill me, but a lot of times there are indirect results as well. Let's say I'm working on a ladder. I'm working on a light here in my office, and I come in contact with electricity. It gives me a shock. The electricity may not harm me significantly, but it startles me to the point where I fall off of the ladder and I'm injured that way. So many times it's the indirect cause, falling off a ladder, coming in contact with the machinery, hitting your head, whatever, because of our response to that stimulus from electricity. So I've got to be aware of what's around me and what those risks are. How much effect, it really depends on what is the current, what is the voltage, what is the resistance. I was really wet one time. I'd been water skiing, and I went to visit. Got done with water skiing. I walked to my dad's shop, and he was out working on a piece of farm equipment with the welder. He'd been welding away, and I walked up to talk to him, and I leaned on the welder, and my skin was wet, and it shocked me really, really good. And I jumped back, and I probably said a word, um, and And my dad said, what's wrong with you? I said, I got shocked. And he walked over, not a good idea to do this, but he walked over and put his hand on the welder and he said, well, I didn't get shocked. What's up? What's wrong with you? Well, the difference was my skin was wet and I didn't have very good resistance. And so the electricity passed through my body, and for sure I felt it. He had dry skin. He had shoes on that would give him some level of increased resistance. And so think about that. Can this electricity pass through my body, and how long will I be shocked as well? All of these are key factors. So just a couple of measurements on this. How much electricity does it take to cause damage? Well, you can feel an electric shock from 1 to 5 milliamps. Milliamps. That's 1,000th of an amp. That's a really small number. How many amps are in that outlet on the wall that I keep pointing out? Well, probably 15 amps. Plenty of power to kill you if they get in the right place. So I can feel it or feel pain at about 3 milliamps. At about 10 milliamps, I have that muscle contraction that I can't let go of the conductor. And that can be really bad because the shock keeps going. Okay. At about 50 milliamps or above, it's going to cause my heart to contract or fibrillate, right? Ventricular fibrillation, it causes my heart to twitch and lose its regular rhythm. At 100 milliamps or above, up to about 4 amps, it's almost always fatal if that gets in the right spot. Above 4 amps, heart paralysis, severe burns. So that outlet in your wall right now has plenty of current to kill you if it gets in the right place. Here are the different types of injuries. Well, let's see. And we want to go through today and talk about the OSHA standards around electrical safety. Now, there are things on from fire code, electrical code, all of those things, and most of them generally reflect the same information. But given that this is an electrical safety presentation, we're talking about the OSHA standards. So you'll see up there 1910 dot whatever. Those are the regulations. If you want to go in and read the specific regulation, this is what I have to do to ensure electrical safety. That's a good place to go. So the basic OSHA standard on this is electrical equipment must be free from recognized hazards that are likely to cause death or serious physical harm to employees. Okay, so our equipment needs to be in good condition. Let's talk about some of the specific requirements that we have under OSHA. So we need to have effective working clearances for our electrical equipment. So if I've got a panel, electrical panel, it needs to be clear of obstructions. That means floor to up to 7 feet above that and at least 3 feet wide. I need to have clear opening. I can't put a cart or a garbage can or anything like that in front of it. That's for a number of reasons. A couple of those are I need to be able to access it in an emergency. If I've got to be able to turn off a breaker, I need to be able to get to it. The other thing is sometimes we have failures in these panels and they can shoot out sparks and sometimes they get really hot. And if I have combustible material stored around that could be the start of a fire and losing our building. So keep those areas accessible. And you can see in here it's beyond 3 feet because I've got multiple panels in this picture. All right. All of our overcurrent protection or circuit breakers, we call them, need to be legibly marked. We need to identify where those circuits are going and what they serve. Well, what if I have a breaker in that panel that we don't use? There's really nothing hooked up to it. It's a spare. Well, you should go to our list there where we're labeling what they serve and put down spare. That is the OSHA standard, and that's the thing they can cite you on. But more important than that is I don't want to be guessing which breaker serves what, because that can cause problems, can cause fires, can cause lots of challenges that way. All right. Overcurrent protection. We talk about circuit breakers. Circuit breakers and fuses as well are designed to protect what? Are they designed to keep you from getting electrocuted? And the answer is no. Are they designed to protect your appliances, the tools that you're using from damage? And the answer is no. Now they may do that inadvertently, but that's not what they're designed for. A circuit breaker will not protect you from being shocked from overcurrent because we already said it's delivering that outlet on the walls, delivering 15 or 20 amps. It's plenty to kill you. What are these overcurrent protections? The circuit breakers designed to protect? They're designed to protect the conductor, the wires that come out of there. We don't want to be drawing so much current that those wires get hot and burn our buildings down. Melt the insulation off of those wires and then cause a fire. So this is why it's really key that we use licensed electricians. If I ever need to install a new circuit, or if there's any question about if we have adequate protection, use a licensed electrician to calculate that and determine the appropriate conductor for what we're using there, the conductor as well as the overcurrent protection. All right, grounding is an essential and key part to our electrical safety. I have to have an adequate ground to keep that power from going where it shouldn't, or if there's a failure in my system, that current goes to the ground. We have big long ground rods that are driven into the ground outside our buildings generally, where it will take that current and safely direct it to the ground. If my ground is broken, that current may go anywhere. It may go places we don't want it. It may cause shocks and electrocutions, or it may cause fires. And so we need to inspect that. You can see here on this picture, this is a simple ground wire at a ball diamond. And it looks like kids were probably out there messing around and they broke that. Well, this is a really unsafe condition. It wasn't on this one, but unfortunately, we had an electrocution of a child from a failed ground and that he came in contact at a ball diamond. All right, let's keep talking. How about our day-to-day interactions with grounding? Well, it's as simple as inspecting our tools. I've got a corded drill or other tool, and I look at that cord and it's missing, or an extension cord for that matter. Somebody's broken the third prong off. Well, it's not adequately grounded. Take it out of service and let's replace that cord so we have adequate grounding. So if there ever is a problem with the tool, you don't become the ground. So inspect your tools. Temporary wiring, we're talking about extension cords. It needs to be temporary, less than 90 days, and I can't be fishing it through walls, going through doors. If I put a zip tie on an extension cord to hold it in place, it no longer becomes temporary wiring. All of those things could be OSHA citations. But more importantly, if I do those things, if I use temporary wiring too long, or I run it through an opening into another room, I could burn my building down from that. And so extension cords have good uses, but they should be temporary. And when we're not using them, they should be unplugged and hung up. And don't use splitters as well. Don't put too much load on that individual outlet. If I don't have enough outlets, we need to request and get an electrician in there and provide adequate service for the stuff that we're doing there, for the appliances that we have. All right, just remember, don't take it through holes in walls and all of that. Our boxes, electrical junction boxes, outlet covers, switch cover, those covers all need to be in place so it keeps us from coming in contact with the electrical connections that are in there. There's one special type of outlet that we see, and this one doesn't look like it. It's those square ones that have the little buttons on it called GFCIs, and it's called a ground fault circuit interrupter. This is a measuring device. So your current goes out through a cord and goes to the appliance, and then it comes back through the white cord. This GFCI measures the amount of current that goes out and comes back. And if there's a difference in that measurement of 3 milliamps or more, it's going to trip. and it's not going to allow the current to go through. This is designed to prevent you from getting electrocuted. We have these in wet areas, places where we could get shocked a lot easier, our bathrooms, our kitchens, or a shop, or outdoors. If we have outlets out there, they should all have a GFCI outlet on them. And if the thing's popping or tripping, that means there's a problem in your system somewhere. It could be wired wrong, or there could be a short, or there could be a problem with the appliance that we're plugging in. Just don't get mad at the GFCI. Realize that that's a problem somewhere in the system. It could be the actual outlet if it's failed, but in many cases it's something else, and that's telling us there's a problem. So don't ignore that. Outdoors, these GFCIs need to have covers. Our tools, we need to inspect those before we use those. You can see on this drill has a separated insulation on the cord. Well, that should be taken out of service and fixed or thrown away. And so make sure those are in place. If I'm working outdoors in a wet environment, or really just I'm working on a construction site, I should have a portable GFCI where I can plug in my tools from that. It's kind of nice that we've switched to mostly cordless now, so we don't have to deal with that as much, but that's something we have to work on. If you work in our public areas, we need to inspect, and fix problems. If you go out to a ball diamond and there's a light standard there, they have a cap that's supposed to be on the pole. Kids like to take those off. If they can get them loose, they're going to take them off. And now if they stick their hand in there, they're exposed to potential open electrical circuits or damaging the ground that could lead to a future electrocution. So inspect your facilities and make sure that they're in good condition. And overall, think. This is pretty risky for us in our jobs, in our homes. Electrical safety is important everywhere. All right. I think we have covered the subject there, and I apologize. I know a little longer than I said I was going to. Just remember, we need to respect electricity. This is universal applicability. Any one of us could get shocked today. Recognize what the hazards are, inspect your facilities, inspect your tools, take a look at what we're dealing with. Let's not have burned down buildings. Let's not have people getting shocked or hurt. As I was preparing this, I went through a list of electrical injuries that have happened over the years, and there were some pretty scary things that had happened over the years, and not just a few of those. So just remember, any of us can be a victim of electricity if we're not paying attention. So pay attention, keep yourself safe out there. Folks, if you have any questions, please type those into the chat box. Find that chat box. Looks like we've got a good group of people here today. Thank you for attending. I just want to, I'll wrap up while we wait for any questions there, and just say, this is a subject that everybody needs to be aware of. This is a good one for dinner time chat with our kids or grandkids or family, whoever we're around, and just talk about how do we manage our safety when it comes to electricity. Oh, and one thing I just realized I omitted a slide there. If we're getting onto buildings, if we're putting a ladder up, look up first, look up and live, and also do not come within 10 feet at the minimum. But depending on the amount of current that we have in a system, if it's a transmission line up there, it's going to be more than 10 feet. But give electricity the distance. All right, I'm looking there. I'm not seeing any chats there. You're making me feel bad, folks. I appreciate you attending today. Appreciate all of your work out there to stay safe and keep all of our people safe in our organizations and your homes. Appreciate all that you do, keeping safe out there. If you want to talk about, let's see, special event risk management, we'll be here in less than a half hour. And if you want to sign up for that, go to utahtrust.gov and click on training and events, and you can sign up there. Thanks, folks. Be safe out there. Have a safe day.